done the part A already last time. So part A was where they were asking us, what is the probability that a randomly selected car will get through Wendy's drive-through in less than 100 minutes? Because remember, they were talking about how long do people have to wait in the drive-through. So just to show you what we did last time on this example, oops. So, they're giving us the mean, which is 138.5 seconds, and with the standard deviation of 29 seconds. Using that, we had created our little bell curve over here on the right, with the standard normal distribution values, that should be mean at 0. And then your 1, 2, and 3 standard deviations above and below the mean. And then using the specific values for mean and standard deviation, we calculated what those numbers would look like exactly with this example. So when they said, people, what is the probability that people will be waiting less than 100 seconds, you can see that 100 value fell between 1 standard deviation and 2 standard deviation below the mean. So we, highlighted that area on our bell curve. The first thing we had to do was calculate the z-score, right? Because we want to know how many standard deviations exactly is 100 below the mean, and we got a z-score of negative 1.33. And then using our normal standard distribution table, which is this guy over here, we were able to calculate that that's a probability of 0.0918 or approximately 9.18%, right? So that was part A. Now let's look at the other parts for this problem. So part B wants to know what is the probability that a randomly selected car will spend more than 160 seconds in the drive-through. So we've already done the less than, we've got more than, and then this one here is actually asking us what proportion of cars spend between 2 and 3 minutes through the Wendy's drive-through. And then the last one wants to know, would it be unusual for a car to spend more than 3 minutes in the drive-through, and why? So, all of these questions obviously want us to calculate the probability, but then they're kind of changing the language a little bit on some of them. And then, we'll have to give a reason for, the answer for that. So I am actually going to go ahead and clear this out so that, those lines won't show up. And let's do the second part, which is more than 160 seconds. So we'll come back to our page over here. This is going to be part B. What's the probability that our car will be spending more than 160 seconds? So the first thing we have to do is figure out, where those 160 seconds are going to fall on our bell curve. So in case you guys don't have your work from last time, I would ask you to go again, draw your bell curve, so that again, you can kind of see where your, shaded area needs to go. So we'll use a different color for our 160 seconds. So 160, again, 138.5 was our mean. The first standard deviation is 167.5. So obviously you can see 160 is going to fall between 0 and 1 standard deviation, more close to 1, right? Because it's close to that 167.5. So I would say maybe, just somewhere over here should be our 160. And since it's saying more than 160, you are shading, to the right-hand side of that. So this is where more than 160 should fall. So that's what we are looking at over here. So same thing, we first need to calculate what the z-score is going to be for 160. So z-score, again, remember that calculation is the data value minus the mean divided by standard deviation. So our data value is 160. Your mean again is 138.5. Standard deviation is 29. So 138.5. And then standard deviation 29. So can you please tell me what our z-score will come out to be for part B? And remember, if your data value is above the mean, you get a positive z-score. If your data value is below the mean, you get a negative z-score. So take a second to do your calculation, and then I'll have you share your value with me. And with z-scores, because the way your table is set up, we always end up rounding to 2 decimal places with z-scores, okay? All right, give you guys just another few seconds here, and then I'll have you share your answer with me. Okay, let me see what you got for your z-score. Okay, Naomi, I see yours. Dennis, Sabri, Eliana, John, Mary. Dennis, you ended up with a negative number. Darla, okay. You've got 160, right? Which is larger than 138.5.
No, I hit a button on my calculator wrong. Sorry, it should be 0.74.
Yeah, okay. Yeah, just to make sure. Very nice, guys. So again, as your raw answer, it comes out to be 0.74, 137. So you're rounding it to 2 decimal places. After the 74, you have a 1. So we know it's not going to change anything for us. So you end up getting 0.74 as your z-score. And then, then we will need to use our little table over here to try and figure out what that probability is going to come out to be. So right now, we've got more than 160 seconds, which comes out to be a z-score of more than 0.74. So think about this again. By default, your standard normal distribution table always gives you the area to the left of the z-score. So, even if your z-score is over here, the table is giving you this entire area over here. And you can actually see that on the positive side, that's what they're showing you. We are interested on the right-hand side, so we will have to do a little calculation to figure that out. So let's start out with our z-score of 0.74. So looking at our table, what area are you looking at for that z-score of 0.74?
Left column 0.7, top row 0.04.
Very good. And they are meeting at what number?
.7704.
Yeah, and I'll make this a little bit larger so it's easier to see. So you will see where those two lines meet. Sabri and John, very nice. So the two lines are meeting right over here at this point. So 0.7704, like Dennis said. Okay. So that is going to be, and I'll actually put it here again in green. So, this is what we got from the table for this Z value. So now remember, this is the area on the left-hand side. So, starting where that 100 was and going to the left is your 0.7704. So since we're interested in the shading, on the right-hand side, remember your entire bell curve is going to be 1. So you end up taking 1 or, put it in decimals, 1.000. And then from this, you will need to subtract this 0.7704 to calculate your probability or your area on the right-hand side. So what do you think this answer will come out to be? And, again, obviously this answer will be in decimal also. And I see there's something on chat. Dennis, yeah, very nice. Sabri, very good. 1 minus 0.774. John, very nice. You will end up with 0. Naomi, Liana, very good. Mary, alrighty. 0.22. Oh, come on, buddy. 96. Alrighty, very nice, perfect. And again, just to make sure, our question was, what is the probability that the car will spend more than 160 seconds? So they're still asking us for probability. So this can be, again, as a percentage, that would be 22.96% if they asked us as a percent value. Normally, again, remember probabilities, we leave them as decimals, but just in case you see a question with percentage, you're just multiplying these number by 100. Alrighty, very good. Now let's go down to part C, which said, what proportion of cars spend between 2 and 3 minutes in Wendy's drive-through? So let me ask you this, since they're giving you the time in 2 or 3 minutes, what's the first thing we should do here?
Convert it.
Yes, since they're giving you minutes, our time is given to us actually in seconds. So let's start with that. So it says between 2 and 3 minutes. So can you tell me what we will rewrite this as in seconds?
$120 and $180.
Very good. Multiply both numbers by 60 because each minute has 60 seconds. So you are saying between 120 and 180 seconds. Okay, so as our notation, you will write this as your X value being between 120 and 180. So of course, start by finding out your Z scores first. So how about we start with 120? What was it? 138.5 for our mean. 29 for standard deviation. Yeah, 138.5 and 29. And then let's find the Z score for 180 next. So I'll give you, again, a couple seconds to calculate both numbers. Just use a comma to separate your answer. And let's see what you come up with. So both Z scores for 120 and 180. All right, guys, go ahead, send me your answers. Okay, Naomi, Dennis, Sabri, Darla, Ileana, Mary. Okay, so now, Dennis, you're missing a negative sign.
Of course, I'm missing my negative sign this time. I forgot to type it in.
Okay. We're gonna have to get your negatives on track here. So again, 120 is smaller than 138.5, right? So that means you should get a negative z-score for this guy. So again, as a raw answer, you had negative 0.63, and then you actually have a 7 after that. So that 7 makes the 3 go up, which gave us the negative 0.64. And again, you guys had that answer. 180, of course, is larger than 138.5. So this guy will, of course, give you a positive z-score. So again, your raw answer is 1.43, 103. So since you have a 1 after the 3, that will not change our value, and we end up with 1.43. Now, as far as what area we are looking at, with your 120 and 180, because I'm going to use purple over here. So 120, again, will be between 1 standard deviation below the mean and of course the mean. So 120, I guess I'm gonna put it almost I suppose halfway between that, and that's a really bad line, but you get an idea. So that's our 120. And 180, as you can see, is going to be between 1 standard deviation and 2 standard deviation above the mean. So, again, kind of somewhere over here would be our 180. So you can see a little bit of that area is going to fall below the mean, and a little bit of that area is going to fall above the mean. So let's take a look at, what this calculation will end up looking like. Okay. So for the area below the mean, that's our z-score of the negative 0. What was that? 64. Let's start with that guy first. So let's go back to our table. On the negative side, so negative 0.64, I am probably not going to be able to bring it all together on the same frame unless I make it really small. And I'm not sure that's going to help you guys out too much. Okay, so let's do this. We know 1, 2, 3, 4, 5. So it's the 5th column, which will be for your, 0.04. So that's the column we're looking at. And then you're looking at negative 0.64 as your z-score. Okay, hopefully that will give you enough to look at. So can you tell me what area are we looking at? Okay, I've got Naomi, Ileana, Sabri, Darla, Mary, John, Dennis. Yeah, perfect, guys. Very good. 0.2611. So this is our line here, and this is our 4.04 column. So yeah, 0.2611. But again, guys, remember, that means from where your z-score is to the left of that. So the area we are trying to calculate is actually from the mean to where your z-score is, because this is part of that area we are calculating, and this is where your negative 0.64 is. So can you tell me how we need to calculate this area for the shaded part? What will we need to do? Okay, Sabri, you said 1 minus 0.2611. That only works if you are trying to find the area to the right-hand side. Because we're not interested in this area either, right? Because this is the other part with the other z-score. So to calculate this area, Dennis, very nice, perfect. So you have to use that idea of symmetry, right? So from the mean to the left-hand side. So let's, will it not let me get rid of this guy? I don't want you. Okay, it's not letting me do that. So this is what we are interested in. So the half from the mean till the bottom is 50% or 0.5. And then from that, you subtract this area of the 0.2611 to find this shaded area that we are interested in. So let's go back to our handout over here. So what we're actually doing is we're finding the probability between 0 and negative 0.64. So this is going to be, as Dennis put it in our chat. Oh, come on, buddy, stop doing this. 0.5, and I'm just going to put that to 4 decimal places to, match our values here. Minus 0.2611. And what will this come out to be? So what do you think this area is going to be? Yeah, very nice. 0.2389 when you do this little subtraction. Okay, so to show you on our little bell curve over here, this is where your mean is, right? So this little area that we calculated, the 2389, is between the 120 and the mean of 138.5. So it's actually, come on, my pen is really driving me crazy. So it's this little area over here, which is your 0.2389. Now we still have to calculate this area, on the right-hand side. So we still need to do that part, which is where our other z-score is going to come into play. So 1.43. Let's take a look at what that will be. So going back to our table, 1.43. And what are you looking at? Okay, Darla. Dennis. So 1.4. And the 3 is over here. So when these guys meet, they are meeting right over here. So yeah, very nice, Mary, John. Okay, Naomi, very nice, guys. 9236. So again, remember 9236 is going to be from where your z-score is all the way to the left, right? So it's going to be all of these areas. So going back to our little calculation over here. So this guy came out to be, what was that number again? 9236. This guy had come out to be 0.2611. Okay, so let me show you that just specifically how you need to calculate this. So here's our mean, or 138.5 with this. Then we had, 180 somewhere over here. We had 120 somewhere over here. So this area over here came out to be our 0.2611, right? And then I guess I'll use horizontal lines all the way from 180 to below it, because that's how the table works. So all of this area, highlighted with the horizontal lines, all of that is the 9236 that we just found. Man. Okay, so as you can see, we are only interested in, we are not going to be using this section over here. So we need to remove this guy. We also need to remove this guy so that we can calculate the area for just this little section, from the mean, because we already know, sorry, that was not 2611. This area here was 0.2389. Sorry, that was for the little guy. Okay, so everything from 120 to the left, so that would actually be this area here. Yeah, because we had to subtract that from 0.5. This area was 2611. This area was 2389. We know together that adds up to half of that, 0.5. So what you will have to do is remove both of these sections on the left-hand side that I've marked with an X, so that we can calculate what the area inside this little red box is going to be. And then once you find that area, you can add it with this 2389 to get the total area between 120 and 180. So it's a little bit of a, figuring out how you get that total area in this case. So we take this value of 9236, and this is going to be for the probability between 120 and 180, which came out to be a z-score of negative 0.64 and between 1.43. So the first thing we are going to do is take our 0.9236. Man, I do not remember to write that too, do I? You will first take the entire area, which is going from 180 all the way to the left. And from that, we are going to subtract what? Since we are trying to find the area between 120 and 180. Yeah, Dennis, very good. So we need the area between 120 to 0 and then 0 to 180. So honestly, the only thing you need to get rid of is this area over here. And that's this number, the 0.2611. So, instead of even doing 0.5 and then coming back and adding, this will be the easiest thing to do, 0.2611. That gets rid of that little left-hand side tail. And we will end up getting our total area between 120 and 180. Okay, so go ahead and do that subtraction, and then let's see what your final answer for that area comes out to be. And the question was, I think, what proportion of cars will spend between 2 and 3 minutes. So this should again be 0 point something. All right, let's see what your answers are, guys. All righty, perfect. And I just realized that I had a bad calculation on mine because my answer looked very different from yours. All right, I see Dennis, Mary, Eliana, Naomi, Sabri, John. Okay, very good. Yeah, guys. So that's giving us a probability, or I guess they're asking it as a proportion, but this is coming out to be 0.6625. And that is definitely going to be our proportion for this. And again, if they ask you as a percentage, which the question is not really asking it as a percent, but that would, be your percent. So again, you can see that's more than 50%. So that means the chances are, yeah, a good chunk of their customers can end up spending between 2 and 3 minutes, which seems like a fairly long time. But again, if you think about it, their mean average wait time is 138 seconds, which is obviously more than 2 minutes because 2 minutes would be at 120. So their average is 2 minutes and some extra time on top of that, almost 2.5 minutes. Well, not quite, 2 1/3, I guess. All right, this was part C, which was in between two numbers. Now part D is asking, would it be unusual for a car to spend more than 3 minutes in Wendy's drive-thru? And then they're asking us why. So, obviously the first thing would be finding the probability of what are the chances that a car would spend more than 3 minutes, and then you would be able to answer this question. So like I said, they may word it differently, but the idea is you're still having to calculate that probability. So let's start by first finding out what's the probability that a car would end up spending more than 3 minutes. So more than 3 minutes, well, let's do it this way, would of course be, what's the probability you're spending more than 180 seconds? Because, obviously we just did the 3 minutes as 180 seconds in this part C. You already have the z-score for 180 because we already did that in part C. And, we came up with approximately 1.43 as our z-score. So again, you don't have to calculate that. And you also have the value from the table of 0.9236. So this time we're actually interested in finding out more than 180. So you can see again, our 180 is right over here. So when we're saying more than 180, again, we're looking at this little portion over here. If I show it to you in this little graph we had done, so again, that would be from 180, to the right-hand side. So what's the probability? So this area was 0.9236. Man, never remember to put that 2 down. 9236. Oh, come on. Okay. So how are you calculating this more than 180? So since we are interested in the right-hand side, what will you do with this 9236? Yeah, very nice, guys. So this is where since everything to the left we have to exclude, which is where your 9236 is, and we're only interested in that right tail, this is the one where you will do the 1 minus 9236. So yeah, very nice, Dennis and Darla. So go ahead, calculate that, and what are we looking at as this number over here? Okay, Darla, I see your answer. Naomi, Dennis. Sabri, John, already, very nice. Mary, yeah, very good. Okay, so 0 point. So you can see it's a small value, right? Because it's 0.0764, or again, as a percentage, that would be 7.64%. So that's our probability here. So based on this probability now, can you tell me how will you answer this question? Would it be unusual for a car to spend more than 3 minutes in Wendy's drive-thru, and why? So what would you say? No greater than 0.05, okay. Dennis, you want to elaborate on that a little bit?
I'm sorry, there should be a comma after the word no. The answer is no, because 0.07 is greater than 0.05, and 0.05 is the cutoff for unusual.
Okay, I see what you're saying. Yeah, Sabri, that was fine. So it is not, yeah, it is not that unusual, because, think about that. When we are saying 0.07 and, this is more than 0.5, so almost 8% if we just round it up. So 8 out of 100 cars, if they are going to be spending more than 3 minutes, then, obviously that's not a very unusual number. Even though your chances are low, it's a smaller probability, it's still not going to be unusual. So yeah, very nice. Not unusual. Like I said, because approximately 8 out of 100 cars will spend more than 3 minutes. Okay, alrighty, guys. So as you can see, this exercise, this question took us through all the different types of possibilities. So in the first one, you just had the less than. And remember, with the less than, it's whatever number you get from your table, you get to keep that, because that's what your table does. When you had greater than, in this case, with the greater than, we ended up subtracting the area you got from your table from 1 so that you could get that right tail. When it was in between, you can see we had to do a little bit of a calculation here to figure out, with the first z-score, you had to do 0.5 minus the value you got from your table to give us that little section between the 120 and 0 on the left-hand side. And then to calculate the area you had between 120 and 180, you actually ended up taking the value you got from the table of 9236. And from that, you subtracted this left-hand area of 2611 that we were going to discard. And that gave you the probability or area between 120 and 180 seconds. So you can see how the in-between calculation was. And then the last one was actually similar to part B, where you had to do the greater than calculation. But then in this case, they were asking you, how do you interpret that answer? Was that an unusual probability or not? So did any of you have any question on this example here? Okay, all righty, very good. So this actually came from sections 7.1 and 7.2, which is what we had looked at last time. Your section 7.4 is actually talking about how we can approximate normal distribution to a binomial distribution. So remember in the last chapter, we talked about binomial distribution, and you guys did that activity, with the coin flip and then coming up with your own binomial distribution table and all of that. So binomial distribution, again, remember, has these properties that have to be satisfied. So you have to have a fixed number of trials. Each trial has to be independent, the outcome. So if you are flipping a coin or rolling a die, every time you do that act, they should be independent. You can have only two outcomes, and we think of them as having a success or a failure. So with your coin flip, if you had the heads that you were looking for, so the heads would be the success. And then if you did not land on a head, which means you landed on a tail, that would be your failure. So two outcomes. And then your probability of success has to remain the same. So these four properties or characteristics have to be satisfied with your binomial distribution. So basically they are saying, you can again see, so they're kind of getting into, a little bit of that description over here. And again, your textbook will also have similar ideas. So we're saying, let's say your probability of success is going to be approximately 0.5. If you think about a coin flip, they are saying as your n increases, and n is the number of trials. So the more times you increase your trials, so just using that coin flip as an example, you had to do 10 flips for each experiment that I had you guys do. But imagine if we started doing, 100 flips, 1,000 flips, 10,000 flips. So increasing those number of trials, we are saying as your n will increase, keeping that probability the same, the shape of your binomial distribution is going to start looking more like the shape of a normal distribution. So it's going to become, very similar to that normal distribution shape. They're saying the larger the n is, and the closer your p-value, your probability is going to be to that 0.5, the more similar the shape of your normal distribution is going to get to, a binomial will get to a normal. And they're kind of showing you this little graph over here. So you can see with your little left-hand side graph, this was more for a binomial distribution. So it's skewing a little bit to the right-hand side, to the positive side, because you've got a little bit more of a tail here on the right-hand side. But as your number of flips increase, you will see the shape of your binomial is starting to look more like a normal distribution over here on the right-hand side. And that's kind of what they are, talking about over here in this little paragraph. And you can kind of read through that. They're also talking about a correction for continuity. They're saying a correction for continuity is a correction employed when a continuous distribution is used to approximate a discrete distribution. Because remember, binomial is based on discrete variables, discrete random variables, we use normal distribution when we're talking about continuous random variables. Remember the difference between discrete and continuous. Discrete is where you can count the values for your random variable. Continuous is where you measure them, right? So height, weight. Discrete would be how many students you have in a class, how many kids does a family have, and that kind of thing. So that's where we talk about this idea of correction for continuity, because obviously you are using two very different types of variables to do this approximation. So there will be some correction you will have to do, and that's kind of where this idea of checking for n times p, when you multiply them, that number has to be greater than 5, or n times q. And remember, your q is just 1 minus your probability p. And so when you multiply n times q is the same thing as n times 1 minus p. So that value also has to be 5 or greater than 5 is what they're talking about. So based on that, what we have to do is your correction actually comes out to be in this form, depending on, what values we come up with. So this table over here, is going to be something you really want to keep handy, or let's take a look at the one in your textbook here. Actually, there we go. So this is where your 7.4 will begin. So another thing that your textbook kind of does is this little checking step over here. So they're actually saying you will have to multiply n times p times q is what our handout is calling it, but n times p times 1 minus p. When you multiply all three of those values, it has to come out to be greater than or equal to 10. Your handout, breaks it up into two parts. It does it in this form, but your textbook just puts it all together. And then we'll talk about the mean and the standard deviation. And remember, you had to do this with your binomial distribution. So that's kind of what they're bringing in over here also, that same idea of mean and standard distribution. So just, what those approximations look like. And here we go. This is what I was talking about. So here's that table that's in your handout also, but you can see how your textbook does the approximation. So this is for that idea of correction of continuity. So, depending on how they ask you for your probabilities, you will have to make these adjustments. If this is what's given to us, this is how we will need to calculate it. So if they're just asking you for one single number, then you actually subtract 0.5 from that number and add 0.5. So that's how you would calculate that little area, in your normal distribution. If the probability is for a number less than or equal to, whatever that A is, in this case, you end up adding 0.5. If you have a probability for a number greater than or equal to A, then in this case, we actually subtract 0.5. And if it's between two values, between A and B, from the A value, you subtract 0.5, and from the B value, you add 0.5. So this would probably be a table I would ask you guys to keep handy, or, create a cheat sheet and put it down on that, however you want to have this. But this will be something you will need for this section in 7.4 for that correction of continuity value. So like I said, this is in your textbook. You can also find it here in your handout. So whichever form you want to use. So this is how, your procedure is going to work. They're talking about check to see whether the normal approximation can be used, find your mean and standard deviation, write down your probability notation. And then based on, whatever your step 3 comes out to be, then you will have to see, depending on what this was, You will then have to put in your correction value in there. So rewrite the problem using that continuity correction, draw a normal curve like we normally do, and then we can start finding our z-scores and our solution. So that's kind of how, this little continuity correction thing works. So let's take a look at an example just to see how we go from a binomial to normal distribution. So this guy is talking about, let's make this a little bit smaller. It has been reported that last year, 25% of the drivers have fallen asleep at the wheel. If 200 drivers are selected at random, what's the probability that 62 will say that they have fallen asleep while driving? So in the report, you have 25% who fell asleep at the wheel. So that's going to be our probability, right? Because that's coming from, whatever report they did. Your n value is your number of trials, which in this case ends up becoming number of drivers. So that's the 200. Remember, your q value is again 1 minus p. So this is where you are taking 1 minus 0.25, and that's how they come up with the 0.75. So again, these guys are having you do it separately, but in your textbook, they will have us do n times p times 1 minus p, and we have to make sure they're equal to or greater than 10. So you can see when we multiply 200 with 0.25 with 0.75, we have to make sure this number comes out to be, larger than 10. And I think you can see it is going to come out to be larger than 10, because you've got, the 200 plus, times these two numbers. So when you multiply these guys, it comes out to be 37.5. So yeah, it is larger than or equal to, greater than or equal to 10. So, that means you are good to go and do a normal approximation. So that was your checking step right over here. Then they are asking you to find the mean and the standard deviation, which again, just to show you in context of your textbook, that's going to be the n times p, and the standard deviation is square root of n times p times 1 minus p. So again, if we had to find the mean, that's n times p, which is the same thing we do over here. 200 times 0.25, which comes out to be 50. Then your standard deviation is square root of n times p times 1 minus p. And you've actually already done this calculation with the checking process, because we already multiplied n times p times 1 minus p, these three numbers, and that came out to be 37.5. So all you're really doing for the square root, standard deviation, is taking the square root of that number. And you can see when you do that, you should get the same answer that you see over here. So approximately 6.12. Once you have this, then the question was asking you, what is the probability that 62 will say that they have fallen asleep? So this is where they're actually asking you exactly for 62. They didn't say anything about more than, less than, at least, at most. None of those terminologies was used. They just said, what's the probability that 62 of them will say they have fallen asleep? So that's actually that first scenario where it's x equals a. And again, remember in your textbook, that's going to be this first one, probability of a over here. So you can see our approximation for this is going to be this guy over here. And so remember, this is where you end up subtracting 0.5 and adding 0.5 to kind of create that in between the two values. So with 62, subtracting 0.5 will put us at 61.5. With 62 added with 0.5 will put you at 62.5. Now remember, your mean was at 50, so 61.5 and 62.5 will fall towards the right. You will take each one of these numbers, convert them to the z-score. So, pretty much the same process we did with part C over here, with this example, because now we know what our upper and lower limit is going to be. And then you are finding your z-scores. You will look at the standard table and find out what the areas is going to be. So you can see for 1.88, we get 0.699. For 204, you get 9793. So in this case, you will end up subtracting the smaller number from the larger one, and that will give us the area in between the two values, between 1.88 and 2.04, and that comes out to be 0.0094, or approximately 0.94%. So it's still less than 1%. So we're saying, there's less than 1% chance that exactly 62 people will say that they fell asleep at the wheel. So remember, this is not about do they actually fall asleep or not. This is about what they will say, right? What they will claim that they did. So we're saying, well, not a whole lot of people are going to admit, right, that they fell asleep at the wheel. And that's kind of what we are saying in this case. So you will see again, guys, there are different types of examples. Now, this one is saying, what is the probability that more than 10 or more people will say they are allergic to ragweed? So now this is 10 or more people. So that's actually an option for number 2 over here, or, I guess it's number 3 in your textbook. So what's the chance that more than 10 people will say that they have, allergies to ragweed? And so again, if you look at this calculation over here, you end up for 10 or more. This is the adjustment we have to make. So you subtract 0.5 from it, and you will see that again right over here. So when it's 10 or more, you subtract 0.5 from that. So that's exactly what we did over here. We're subtracting 0.5. So you're actually finding the probability that it's going to be more than 9.5. So, same thing, take your 9.5, find its z-score, based on the mean and standard deviation you come up with, negative 2.48. And remember, since this is more than, this is the area we're interested in, but the table will actually give you that little tail on the left-hand side. So you will notice we end up subtracting the number from 1.000, and you have 99.34%. So 10 or more people having an allergy to ragweed it's a good chance, 99.34% from a sample of 200 Americans. So, that's kind of how this works. So look at the different examples you have over here. When they're saying at most, that means the maximum you can have is 26 hits. So you will see now this is going to be an example for less than or equal to. So this is where you actually add 0.5 to it. So now you're looking at a probability of X being less than 26.5. So, less than, you just find your z-score, whatever area you get, that's going to be your answer, because your table always gives you the less than. So that means in this case, you're going directly to 0.1190 or 11.9%. So really the only thing, your calculations and everything are going to stay the same. The only difference is going to be when you first come up with your probability notation, you will have to make that approximation based on your correction for continuity. So the only difference is going to be once you come up with this little notation over here, make that adjustment based on this correction table over here. And then once you have these approximations, defined, once you come up with these guys, then you can go back and do the same calculations that you do in section 7.2 to come up with these values over here. And you can kind of, again, your textbook also has examples on this, and then your handout also has a bunch of different examples to help you out with those notations. So what I would like you to do is, again, work through your homework for these sections, so that way you can again have a chance to ask me a question before you do your exam on Wednesday next week. So this is all of chapter 7 up until this point. Now, honestly, I don't know why your textbook did that. They put the central limit theorem, instead of putting it in chapter 7, they put it in chapter 8. So let me just show you that very quickly. And that's kind of what they did over here, is brought that idea of the central limit theorem right here into chapter 8. So we'll take a look at this next time. I'll just get you a little introduction on this, but I actually also have an activity for us to do, just to give you a little bit more hands-on practice with normal distribution. So we'll look at chapter 8 on Monday, and then we'll do that little in-class activity. And then you guys should be ready for your exam on 7 and 8 for next Wednesday. So again, guys, please do not fall behind. You have no discussion posts and no activity like we did with the other chapters. So you should be spending all that extra time finishing your My Stat Lab homework. So if you have any questions, stay behind and ask me that. And if not, guys, then I will see you on Monday afternoon. So good luck, everyone. Have a wonderful weekend and be safe. Take care, guys. Be
Have a
careful,
good weekend.
everyone. You too. Thank you. Hey, did you guys have questions for me?
I did, but it's